So welcome back. Previously, in our last video, we figured out that the mass of the planet was about 10%. We were about 10% off from our original mass that we had in our code. And the reason for this is because we had envisioned that the sun was at the center and the planet was orbiting around the sun. But if you remember looking at the code, we see that we have the sun and we have our planet over here. But if you look closely, it seems as if the sun is also orbiting around a point that is between the sun and the planet. And this point we end up calling the barycenter. So to get a more accurate planet mass, what we have to do is change a few things. Now, everything here that's written in this yellow ink is no longer gonna work for us anymore, because we're now gonna use not only the radius of the planet, which now we're calling this radius of the planet, to this point where both of them seem to be orbiting around. We're also going to include the radius of the sun to this point. So now that we have, I said we're going to use this radius of the planet and this radius of the sun. Again, all this is not going to work anymore. And we're going to start from scratch again from this acceleration equation. So, Jamor. So we're also going to erase the velocity of the planet, because that is no longer going to work, because this velocity was for the planet orbiting around the sun. But now that we have this new model where we have the sun and the planet orbiting a point between them, so our sun is going to be orbiting around this point, and the planet is also going to be, they're both going to be orbiting around it in sort of this fashion. So we're going to have, again, this distance, we're going to call it the radius of the planet, and the distance from the sun to this center spot, we're going to call it the radius of the sun. So let me erase this over here, because we no longer need it. So again, this is going to be the orbit radius, not the physical radius of the sun or the planet. It's to that point, which is called, we call this, again, the barycenter. So in order to implement this new barycenter, what we're going to do is go back to, like I mentioned, this equation, which we got from working out the forces of the planet, of the sun on the planet. And we're going to rewrite this equation as acceleration of the planet is going to equal g ms, mass of the sun, divided by, now it's not only the radius of the planet, but we're going to add the radius of the sun. By radius, I mean this, from the sun to this barycenter, plus RP, and we're going to square that. So now we're using the radius of the sun plus the radius of the planet, because this is the distance between the two objects, which is the sun and the planet. We have RS plus RP.
And our object, remember, is still undergoing uniform circular motion. And for uniform circular motion, the acceleration is supposed to be equal to the velocity squared divided by the radius. Now we can ask ourselves, what velocity is this and what radius is this? So let's take a moment and pause for a second. This equation, the left-hand side, is talking about the acceleration due to gravity on an object, the object being the planet itself. that acceleration is experienced between the locations of the objects. So the reason we used rs plus rp, as Daniela showed us before, is because the distance from the center of the planet to the center of the star is rs plus rp. However, here, when we talk about uniform circular motion, we're looking at one object orbiting around a central location. And remember that our central location here was given by the barycenter. So putting this all together means that the velocity we care about was related to this object, the planet. So this must be Vp. And this r is actually just Rp, and no longer is it Rs plus Rp. Again, that's because the planet is orbiting about the barycenter. So we want to use the radius to the barycenter. Now, just like before, we can substitute in for Vp squared. Because remember that Vp is just equal to 2 pi Rp divided by the period. Remember, distance divided by time. So if I plug this in, this equation looks like 1 divided by Rp, I'll pull out the front, times 2 pi Rp over T, everything squared, which I will just carry on to the next line and say that this is equal to 1 over Rp times 4 pi squared Rp squared over T squared. And it shouldn't be a surprise to you that one of these Rp's will cancel. So we'll get rid of the 2 up here and get rid of the entire Rp from here and have that this quantity now, I'll rewrite it just for simplicity, GMS over Rs plus Rp, both of those squared, is equal to 4 pi squared Rp over the period squared. And I can simplify this further and multiply both sides of my equation by Rs plus Rp squared. I'll have it here once and I'll have it here once. So times Rs plus Rp squared GMS over Rs plus Rp squared is equal to 4 pi squared Rp Rs plus Rp divided by the period.
Squared.
Yes, thank you. Squared. So these cancel, and we're left with this 4 pi squared Rp times the quantity Rs plus Rp squared divided by the period squared. And in one more step, I will move some things over to make this look more explicitly like a cubic equation. So if I multiply now both sides by t squared divided by 4 pi squared, I will get that t squared over 4 pi squared times gm equals, in one step I will do t squared over 4 pi squared times 4 pi squared Rp Rs plus Rp squared divided by t squared. So on this side, the 4 pi squareds cancel, and the t squareds also cancel. So now what's left on the right-hand side of this equation is simply Rp times Rs plus Rp squared. So now what's left on the left-hand side of the equation is t squared over 4 pi squared times gm. And we already know all of these individual numbers. T was calculated before, and G and M are given to us in the beginning of the code. And on the right-hand side of the equation, we have Rp times the quantity Rs plus Rp squared. It's clear from the setup here that we now have a cubic polynomial in terms of Rp. But the one thing we're still missing is Rs. So to get Rs, we're going to use a similar setup that we used to get Rp before. V S is equal to 2 pi RS over period. And VS is right here above us. We have the 5.77. 2 pi is a number, and the period we know is 18. So if I move things over and simplify, we get that RS is equal to the period times VS divided by 2 pi, which is equal to 18 times 5.77 divided by 2 pi. And for that number, we have, and that gives us 16.5. Okay, so now that we know RS, we can plug that into this equation and solve this cubic polynomial to get RP. We've left a link in the description to Wolfram Alpha, which is an online calculator you can use to actually solve and figure out what RP is. And when you take that RP and you go through the same steps we did in the last video, you find that the mass you measure for the planet is about 0.2001, which is very, very close to the value we had given to us in the beginning of the code.
And we did it!
Yes, we know the mass of the planet. So now astronomers can go out there and look for extrasolar planets simply by doing the same calculations we just showed you how to do. We hope you learned a lot and that you'll join us next time. Take care. Bye.
See ya!